Hello and welcome to our today's webinar, Practical Aspects of Wavelength Dispersive Spectroscopy. Our application specialist, Julia Maus, will show you today several application examples where EDS measurements reach their limits. And WDS is therefore a very important tool to improve your results and get correct ones. She will also show you how easy it is to work nowadays compared to the past with WDS systems and how to optimize the measurements. Julia started over 3 years ago at Ametec Idachsgarten in Germany. She is the application specialist for EDS and WDS and works primarily in our demo labs in Munich and Weiterstadt, which is close to Frankfurt. She is responsible for our in-house training courses, but also for on-site trainings. Beside demonstration of our EDAX product portfolio, EDS, WDS, and EBSD, she supports workshops and conferences and is a very important part in helping our customers in technical and application-related questions. Before we now start, here are some general information. You can submit questions during the presentation through the question panel. We will answer your question after the presentation, and if the time is limited or there are too many, we will answer after the webinar by email. And now I will hand over to Julia for the presentation. Enjoy.
Thank you, Michaela, for the kind introduction, and welcome also from my side. Today, I would like to talk about the practical aspects of wavelength dispersive spectroscopy, or WDS in short, and we will look at use cases, setup, and also at optimization. First of all, I would like to give you a little introduction for those of you who are not so familiar with the difference in the techniques. At first glance, these two spectra might appear to be ordinary EDS spectra. Both show an intensity distribution across a given energy range, and you may also notice that the absolute signal intensity difference between those two. For an untrained eye and without element identification, it can be quite challenging to realize that these spectra are indeed from the same sample. When we overlay the two spectra, the difference becomes much clearer. They represent the same data, but with vastly different energy resolution and peak-to-background ratios. While the signal originates from the same sample, the red spectrum was collecting using EDS detector, whereas the blue spectrum was obtained with a WDS detector. The discovery of X-rays by the German physicist Wilhelm Röntgen dates back around 130 years. This breakthrough marked the beginning of a new era in science and technology. However, it was not an overnight transformation. Over the decades, many scientists contributed to the understanding and properties and behavior of the X-rays. And significant technological advancements were required before we could analyze samples as we do today. The first commercial energy dispersive spectrometer systems appeared in the 1960s. Just a few years later, the first commercial wavelength dispersive detectors were introduced, paving the way for even more precise analysis. If we look at the signal origin, both EDS and WDS are based on the detection of characteristic X-rays. The incoming electron beam causes an inner shell ionization, which can undergo two main de-excitation pathways. Each option has a characteristic energy signature, which depends on the electronic structure of the material analyzed. For both EDS and WDS, only the resulting X-rays are detected. Depending on the element, different transitions are possible, and so the principles of excitation, signal generation, and the underlying physics are actually the same for both techniques. However, the way these signals are detected is fundamentally different. So let's look at the signal detection of each of those techniques. In an EDS detector, incoming X-rays are absorbed in the silicon chip, as shown on the bottom right, by means of photoelectric absorption. This interaction generates electron-hole pairs. Due to the applied voltage, these pairs are then separated. And what's really nice is that the number of electrons produced depends on the energy of the incoming X-ray. The higher the energy, the more electrons are produced, and the lower the X-ray, the fewer electrons are produced. Looking closer at the readout of the voltage of the EDS detector, we can see on the right-hand side some noise followed by a steep voltage increase proportional to the respective energy. When learning about the EDS and WDS for the first time, the difference between the two techniques is often mentioned that the EDS detector can detect energies at the same time. Phrasing it this way can be a bit misleading. If we examine the graph, it becomes quite clear that the detector processes one signal at a time. It does not truly multitask. The detector can distinguish between different energies without physically changing the detector. The acquisition and processing of signals happens so quickly that the signal to the eye appears to be at the same time. So let me quickly show you how fast the EDS signals are processed. When I click in the navigation image, the EDS acquisition starts immediately. The elements get labeled automatically, and when I switch to another location, it starts the collection again. At no point you see individual signals appearing. It's always the full spectra, at least visually. The detectors used in WDS systems are proportional counters and, as the name implies, are extremely good in counting. They really only do count and cannot distinguish X-ray energies themselves. The energy selection therefore must be done before the detection. In contrast to EDS, not all energies are collected at the, let's say, same time. It's done in sequence, so one after another. The energies are selected using flat crystals with a defined lattice spacing. Once the collimated X-ray from the sample reaches the crystal, they interact with the atomic lattice, and following Bragg's law, high energies are diffracted under a different angle than lower energies. So by positioning the proportional counter under a given angle, the respective energy can be measured. The proportional counter needs to be calibrated also by the user, using the pulse height distribution. This relates to the response behavior of the proportional counter itself. This is typically done with single element standards, and one key parameter here is to adjust the height voltage applied. Changing the high voltage affects both the height and the width of the distribution, and the user must ensure that the pulse height distribution stays within the defined limits and none of the signals is cut off. The pulse height distribution might shift with changes in count rate. To make sure chosen high voltage settings work well, it's best to test it under extreme conditions. First, at high count rate, which I usually do using high beam current settings, and then at low signal levels, where I just turn down the beam current as much as I possibly can. This helps to confirm that the detector responds linearly across the full regime of operation. When the system is installed, the service technician performs a broad calibration, but the user must fine-tune the calibration, especially for uncommonly used elements. For EDS, we typically work at the microscope's analytical working distance. However, WDS requires much more precise sample height alignment. This process is guided by Apex automatic height alignment tool, where the stage set position is varied while recording the intensity changes for the given energy. Once this is completed, the software determines the maximum of the peak and places the stage on the respective set position. It's important to note that the curvature for these plots are not the same for all crystals. In theory, the peak position can be determined precisely, but in practice, the graph often contains signal fluctuation. So when the curvature is flat, it becomes much harder to identify the optimal height position. Crystals with low lattice spacing, those correspond to high energy X-rays, are used for height alignment because this allows for a much more precise placement, and all the lower energies can then be measured afterwards. The other way around, if a low energy line is used for height calibration, it does not guarantee perfect alignment for high energy measurements. What I therefore recommend is to let the software guide you with the selection of the energy used, or manually select the highest energy with decent intensity present in the sample. Not only the stage height is important to adjust correctly, but also the magnification. Each crystal has a different field of view from which signal reaches the detector. Low lattice spacings and, again, high X-ray energies have a much smaller field of view than lower energies, as illustrated in the image. In some cases, too low magnification settings only result in unnecessarily long measurement times. However, for quantitative and qualitative analyses, it can drastically distort the results. For example, the quantitative points 1 and 2 in the image on the right will differ significantly from each other, not because the composition changes, but because the signal loss is substantial. Apex will warn you if the magnification setting is too low and guides you towards higher magnification settings. Nevertheless, it's important to understand which magnification range each crystal has and to apply them correctly. So how do we strategically combine EDS and WDS? As the EDS and WDS go together hand in hand, we use the EDS to get an overview over the sample's composition and identify possible elements. Then, the WDS is systematically used to investigate trace elements, analyze peak overlaps, and quantify the presence of those elements. In case quantification is needed, I commonly quantify all the major elements with EDS and then use the WDS for the elements with overlaps or traces. A common example here with silicon is the presence of tantalum and tungsten, as shown in the image. EDS alone is not very helpful, as those peaks are so close by that small concentrations of tungsten or tantalum in silicon are hardly recognized in shape changes with the EDS. On the other hand, when the detection limit of the EDS is on its limit, I can use WDS to investigate in low concentration elements. In the example shown here, cobalt and iron signals are overlapping, and on top of that, cobalt has a very low concentration. This can only be measured with the WDS, as the signal is again so low that virtually no effect on the peak shape of the EDS is seen. In the next section, I would like to show you some examples of WDS maps. For WDS, we can scan data in 3 general ways: a full scan, a reduced scan, or only the peak position. Quantification can be done with both full or reduced scans, but for mapping, we only ever use the peak position, as elsewise the map would take too long. Depending on the energy and the crystal used, the energy resolution can be very high, leading to peaks of only a few electron volts in width. For mapping, still only the peak position is used. So why is this relevant? Well, small energy shifts in the range of 1 to 3 eV in a full or reduced scan do not really affect the measurement, as the intensity is still within the measured range. For the peak position of a high energy resolution peak, even shifts of 1 or 2 or even 3 eV can cause an extreme signal loss. The easiest way to prevent that is taking a full energy scan over the peak prior to the mapping. Apex allows to alter the peak position used in mappings for a given setup. Okay, let me show you how to take an energy scan before we collect a map in Apex. I first choose the region of interest in the navigation image and then start the EDS preview. I can already indicate the overlay of several elements in the spectra. I can zoom in the EDS data and mark the energy range I want to be using for WDS. I like to specify it a little bit more precisely now by typing start and end energy for my given scan. The dwell time is set to 1 second, and then I can start the collection. Now the motor is bringing the crystal into position, and we continuously scan through the energy range. You see the data appearing on the right. Let me just jump a little bit in front. Now you see continuously building up the data, and once it's complete, we can identify all the elements present in the spectra. The WDS energy scan, which we just took, show us the intermixing area and reveals the presence of tantalum, silicon, rhenium, and iridium. I can use this for optimal peak positioning of the WDS maps, and it can also be used to adjust the background positions, which I will show in a bit. Now we want to map the regions we have just measured with a point measurement. Let me show you how to set up a simultaneous EDS and WDS map. The navigation image is already collected, and I first need to specify which elements should be mapped with a WDS. So here I chose silicon K and tantalum M. Both are measured on diffractor number 5. The peak of both elements is already adjusted so well that I don't have to adjust the peak position. For the mapping parameters, I only reduce the number of frames. When I start the map, I can choose the elements used in EDS mapping. These can also be changed after the measurement or during the live acquisitions. Once I have decided what I want to map, I can then say OK, and the measurement will start. Now I will jump a little bit ahead, as the collection will take a few minutes for you to see the results. So when we jump a little bit ahead, it starts the collection of tantalum first, and once tantalum is finished, it will start the mapping of silicon. So the intensity is just continuously added up. When we go a little bit further in the video, we start to see intensity of the silicon to appear, and we collect more and more statistic over time. Once the maps are completed, we get a set of different elemental distributions, and I can mix and match the overlay between EDS and WDS. That, of course, saves me time because I don't have to measure every single element with a WDS. I was going a little bit fast through the acquisition. I only intended to show you basically how it's set up and how easy that is. I want to highlight something more that was not so easily to be seen. When I started a map, the remaining time was about 13 minutes for the tantalum map and the silicon map. After around 2 minutes, we already see a distribution of the silicon very close to the final distribution of the image. It visually matches already pretty good. That's extremely fast. After 2 minutes, we already get a distribution that reveals us the true distribution of silicon in the sample. Looking at tantalum, of course in the spectrum we already saw the intensity is much lower than silicon. Hence the map also takes longer until we get a good representation of the distribution. After around 8 minutes, it's pretty clear and the distribution matches what we see in the final map after around 13 minutes. For silicon and tantalum, the true elemental distributions are only revealed using WDS due to the very strong overlay. So when I now present the results, we can compare. On the left are the EDS raw data maps, and to the right of it we can see how much of a difference it makes when we measure it with WDS. So the consequences are quite drastic, as the message to, let's say, our development department might differ depending on which of those two maps we provide to them. Even though I have not shown it here, for iridium and rhenium that's the same. The true distribution will only be revealed with WDS maps. I have a few other mappings I would like to show you and discuss what's relevant about EDS and WDS maps. Now we're gonna have a look at lithium manganese iron phosphate samples, which is commonly used as a cathode material in lithium ion batteries. The raw intensity distribution in the EDS maps, or so-called ROI maps, are shown for each iron and manganese on the left. The EDS spectrum on the right shows us the overlapping L lines which are used for this mapping. For the ROI, the respective energy range used to display iron and manganese in the mapping is highlighted in the spectrum with matching colors. There is a clear double peak shape present, which allows the data to be separated without further processing. The map shows clean separation as illustrated with the little iron particle on the left-hand side, which is not present in the manganese mapping. Okay, now the interesting element for this material is actually fluorine, as its distribution is relevant for the cathode's behavior in the electrolyte. The raw EDS map displays a strong intensity with homogeneous distribution. Now the question arises, how well this fluorine distribution represents the true distribution in the map. Looking again at the energy range used for the EDS maps, we can see that also the fluorine is in the same peak position as manganese and iron L. Fortunately, I measured the sample with WDS, here in red as well. It reveals that under the iron and manganese signal, a tiny fluorine peak contribution is hiding. Now, the data for all three elements strongly overlaps. This means wherever iron is measured, or manganese is measured, the map will display fluorine as they are in the same range. So let me show you a comparison between the different data sets. On the left-hand side, we see the raw data fluorine map. In the middle, we see a deconvoluted background corrected map of EDS. And on the right-hand side, we see a WDS map. The messages in each of them are quite different. Important to note is that all the maps were collected at the same time. So while in the EDS map the distribution is rather homogeneous, in the WDS map we can see there's a clear enrichment on the surface of the sample. I will talk about the net map of the EDS in a second. For now, we somehow see a similar representation as with the WDS map, but we can also see that the noise level in it is extremely high. And without having the WDS map side by side, I wouldn't have trusted that map. Okay, in this graph I want to illustrate the source of error for these EDS maps. And the WDS map as a guidance is put below, so that I know from where to extract the EDS data in the different pixels. On the first two images, I was summing up the pixel intensity of multiple pixels. What we can see is that in the low fluorine region, we see a double peak shape for around manganese and iron. And in the high fluorine content region, we see a peak shape change with an actual increase of the fluorine. Well, this is very visible. However, if we look at the per pixel data of the EDS, we can see that the noise around this peak is extremely high, and the per pixel data has a hard time distinguishing the peak shape and do a deconvolution, as well as a background correction. We can also see that the background subtraction has a large error, and small statistical fluctuations add to a huge error on the deconvolution. A major part of the analyst's work with WDS lies in quantifying the present elements. When we're working with EDS, we are very used to get quantification results immediately. Those are called standardless normalized quantification results. I've shown you here a little bit of the math. We don't need to go into detail here. What's really important is when we identify all the elements in the spectra, we can get a quantification out of this. It's an underdetermined system, hence all the elements must be identified that are present in the sample. When we measure the sample with WDS to perform quantification, we only measure a fraction of the full spectra. The full scan scans the full peak of interest, including some background positions. The reduced scan is used to save more time in the measurement and leaves out quite a fraction of signal and background locations. As we don't get as much information out of the spectra than we get with EDS, the quantification always requires a standard and a sample to be measured under the same conditions. So a full K-ratio protocol has to be followed. Apex Full Standard Quant menu offers some tools to handle your standards in a database, which means you can load and access them at any time. What I want to focus on now is that for quantitative work, it is extremely important to calculate the net intensity correctly. Apex has a default background position for all elements, which are at certain distances from the peak. It is impossible for us to find a default background location that fits all elements and all element combinations used. Therefore, the user needs to verify that no other peak lays within the background location. On the image, a reduced scan is shown, and it's really difficult to judge whether or not the background location collected here is valid. So let's have a look at the background position collected with this scan. Looking back at the full energy scan, we can see that the right background location lands on the right shoulder of the titanium peak. Much better would be to choose a location further to the left and right to make sure the background signal is recorded correctly. Generally, I recommend to perform a brief energy scan before you acquire any data. Doesn't matter if it's mappings or quantification, to really be sure there is no signal present. The simplest quantification is done using single element standards for each element present in the sample. Let me show you. First, we need to determine the reference measurement on copper, which is used to bridge the geometrical conditions between EDS and WDS. After the collection is finished, the reference value will update in the software and be used for all the future measurements. Then I move the stage to the Faraday cup position to read out the beam current. I manually read out the beam current, but this can also be done automatically. The height alignment of all locations were determined prior to the acquisition of the data and saved on the microscope side. Now I move to the first standard where I measure copper. Here I edited the start and end energy as well as the dwell time. Then I hit collect. Now the motor will move the crystal into position and start the collection of copper. We collect a few background positions before and after each peak. So in this case, copper. Okay. Now I move the stage to the second standard, which is zinc, and repeat the process. I collect the navigation image again. Select zinc and start the measurement. Now the data acquisition of zinc takes place, and we see that the intensity is nicely within our reduced area. Once this is collected, I go to the stage location of my unknown sample and collect the data there as well. If I do an EDS preview, I can clearly see it's brass. Then I select the two elements I want to scan in this location. I check if the energy ranges are correct and adjust the dwell time for my reduced scan. And then I collect the data. The system will automatically do one first and then the second, moving the crystals in the most efficient way. And once the data is complete, it appears on the project tree and I can rename it for further use. Now we have collected the data sets. Now let me show you how to quantify WDS standards. First, we need to open the data set of the first standard, give it a unique name. I usually like to add the voltage used and the line, the transition line I have picked out. Then I need to save the standard. The target composition is already set to 100%. And repeat the step with the zinc standard. So I give it again a unique name, specify the KV and the technique used. Then I again need to specify the target composition, which is again 100%, saved the standard, and now I can use the standard saved. Therefore, I have to open the saved dataset I want it to be applied to, and I need to tell the software among my database, which you can see here, which of the standards I want to be used. I have collected another set of standards, which contains the K-line here, so I can show you the difference in those two. Okay, when I'm happy with my selection, I'll tell the software that I want to use the standards for quantification, and I initiate the qualification process. Now you can see the sum goes very nicely to almost 99%. This is a good indication. And these were the EDS standards, and when I flip the method, you see it indicated with the little symbol. I use the L lines and I result in around 95% total. The best benefit you have about the full standards quant is that EDS and WDS data is always saved together, and you can mix and match the signals you want to use. You can see that in the picture under the method icon. The little lambda symbol indicates that the WDS standard was used, while just the spectrum indicates that the EDS standard was used. This saves you a lot of time because you don't have to measure all the elements present in the sample. I have not shown it here, but you can use compound standards as well. So I hope my webinar was useful to you. If you are looking for more resources about EDS, EBSD, and WDS, please have a look at our blog and on upcoming webinars on the website. If you have any open questions, please, as Michaela mentioned before, use the possibility of the question panel. I will try to answer as best as I can. And if we cannot answer all questions, we will certainly reach out. Okay, thank you very much for your attention. That was today's webinar. And now, Michaela, let me know if there's any questions.
Yeah, thank you, Julia, for this interesting presentation here. And we got several questions in the chat. Maybe we start with one of them. So we have here, for EDS, an energy calibration is regularly needed. How often does the WDS need to be calibrated? And how is it done? I think that means, can the customer do it by themselves, or is service needed? What is, how important is it? How often needs to be done, the calibration?
Okay, no problem. So when the WDS is installed, our service technician will perform an energy calibration of all crystals. We'll also calibrate the optics to be placed in the optimal spot. And we'll also do a broad calibration of, for example, the HV, as I mentioned in the talk. What's important for the user to do regularly is especially the HV calibration once you start to use a new element that has not been optimized prior to that acquisition. Once this is done, usually the response is extremely stable and doesn't have to be checked again. On the other hand, the energy calibration can fluctuate between 1 or 3 EV, but it's extremely stable and should only be performed by our service technicians.
Thanks. I think this answers quite well here this question. And so how much gas does the WDS need? So we need this P10 gas, which is a mixture of argon and methane. And here's a question, how much of these do we need? And also, if we can exchange the gas, can we use helium or xenon or something else?
Yeah, good question. I didn't mention it. I talked about how we detect the X-rays in the WDS and that we use a proportional counter. Therefore, we need P10 gas, and we only operate our WDS systems with P10 gas. So no, we cannot use xenon or other gases. The consumption is in the order of roughly a liter per hour. And a small gas bottle, really small gas bottles, let's say 20 liters, will last very long.
Yeah, it depends how often you do WDS measurements, right? Is there also something that you have to turn on the gas quite early before you do a measurement?
Yes, so definitely the gas should be turned on prior to the data acquisition so that the detector can be flushed and in stable operation. I usually wait 15, 20 minutes before I start the measurement.
Another question was here about standards. Which standards can you recommend for WDS measurements?
That's a bit of a tricky question. There's multiple standards you should have available. I mentioned the HV calibration, and best for it is to use single element standards. I know not all elements have single element standards, so you should have a set of single element standards to perform that calibration. On the other hand, when you perform quantification, you would have to have a block of standards that match your samples well in terms of quantification. And you need to make sure that the manufacturer from which you purchase those standards are of good quality. So there's a couple of manufacturers out there from which you can purchase them. I have an array of 52 mineralogical standards, which I can then use if I do analysis on those kind of samples. And on the other hand, I have a block with single element metals and binary compounds. But for optimal quantification, it's really important that you have a standard that's really close to the samples you measure.
And I think if customers have here special questions, they can easily reach out to you, to us here, and we will support as good as we can. Another question was here about, can some elements be measured on multiple crystals? And how does the software choose it?
Yes, you can measure not all, but some of the elements on multiple crystals. And that's actually a huge advantage because you can choose between better resolution, let's say, and higher intensity of the peaks. And the software indicates these settings. This comes down to what you want to do. I generally try to aim for higher intensity as a default setting. And when I see that I have a very close overlay with the peaks, I just select higher resolution.
Okay. Yeah, this answers the question, I think, quite well. Thanks. I think we answered most of the questions for today. It's quite a long meeting already. So I thank you all for your attention, joining our webinar. Wish you all a good day, especially thanks to Julia, and hope to hear you in the next webinars. Okay, thanks. Bye.